So a pipe of 20 mm diameter carries water at velocity of 1.5 meter per second, and then calculate the Reynolds number for the flow and determine the flow regime. So the viscosity is at 0.001, and by using formula Reynolds, rho Vd over mu, so we have the rho of water, that is 1000. So rho is typical value, kilogram per meter cube. And then we have velocity given in the question. So velocity 1.5 meter per second. And then we have the diameter, so 20 mm. And then we have the viscosity 0.001. So what we need to do? First, you need to convert the mm into meter. Okay? And then the second, alright, so we just put all the values into this formula, and then you will get 30,000. So when by looking at this range, so 30,000 is higher than 2,300, so meaning that it is turbulent. So the flow regime, so the Reynolds is larger than 2,300, so meaning that the flow is turbulent. And then velocity and discharge. So velocity is a parameter that tells how fast and what direction the fluid flows. Okay, it is measured by meter per second unit here. And then for the discharge, we have meter cube per second unit, and it is a total quantity, volume meter cube of fluid flowing in unit time. Okay, unit time per second, past any particular cross section of a stream or pipe. Okay, so we have volumetric flow rate, Q. The symbol is Q. So the basic formula, a very basic formula for the Q, for the fluid mechanics. Okay, so you must remember to calculate the Q flow rate by formula A times V. Okay, so Q equal to A times V. So after this, you must remember, you must put it in your mind. Okay, tak ada dah nak teka-teka dah. Okay, so Q equal to AV. And then mass flow rate, mass, okay, kilogram per second, okay, M equal to the rho times Q, and then the weight flow rate, W, is rho times gravity times flow rate. So let's look into this example. So the benzene flows through a 100 mm diameter. Okay, the velocity is 3 meter per second, and then you need to find the volumetric rate, weight of flow rate, and mass flow rate. Whereas the density given 879 kg per meter cube. So first you need to calculate the area. So area of the pipe by using formula pi d square over 4. So since the diameter is millimeter, so you need to convert to meter. So then you will solve, you get 0.007854 meter square for the area. So again, by using the basic formula of flow rate, Q equal to AV. So A is calculated before times the velocity given 3 meter per second. So you get 0.0236 meter cube per second. So then you calculate your M. So here is M, yeah. So this one, M is equal to rho Q. Okay. So this one, M equal to rho Q. So rho is 879 given, and then times with the Q. Q is calculated before 0.0236. So please calculate the new value. Okay, so this is some error here. So the the new value, and then you calculate your W. So this is W. So W is rho GQ. So rho GQ here. So we have rho is given 879 times with Q times with G. Okay, 9.81 times with the Q. So Q is here 0. Okay, so you will have your W here. Okay, so this one 0.203 ni value untuk W. So this one that value untuk W. Okay, so some error here. So 0.203 kita ada kat sini. So yang you nak kena correct is M equal to rho Q. Yang ni tak ada kira lagi. Okay, so now we continue with average velocity for a full flow in closed conduit. So closed conduit means a circular pipe having the liquid that flowing fully into this pipe. So this is the side view of the pipe, and this is the cross section of the circular pipe. So the fluid molecules that flowing in the center of the pipe have the highest velocity as compared to the molecules that near to the boundary of the pipe. So the radius of the pipe is R. Therefore, the area of the circular equal to pi r square. And then the volume, the flow rate Q equal to the velocity of the fluid times with the difference of area, because difference area may have the difference of the velocity. And then we integrate the flow rate to the radius. So therefore we get the average velocity equal to Q over A. So therefore the basic formula to calculate the flow rate, Q equal to area of the circular, area of the pipes times with the velocity. So A is cross-sectional area of the fluid flow times with the V, average velocity. So now we move to conservation law applied to control volume, CV. So there are three categories. First, the conservation of mass, momentum, and energy. So any conserved quantity must be balanced. So let's look into this. So conservation of mass equal to the mass of fluid that entering per unit time equal to the fluid leaving per unit time plus the increase of mass of fluid in the control volume per unit time. However, for the steady flow, fluid mass in control volume is constant. So for example, this is the control volume. Previous example, we have nozzle. So let's say this is a nozzle. So the mass of fluid entering the nozzle or control volume equal to the mass of fluid that leave the nozzle. So for the steady flow, we have the mass of fluid entering per unit time equal to mass of fluid leaving per unit time. By applying conservation of mass to a steady flow in a stream tube having a cross-sectional area small enough for the velocity to be considered a constant, so therefore for the region between section 1 and section 2, since there can be no flow through the walls of a stream tube, therefore the area at section 1 is A1, and then velocity that pass this section 1 is U1 and the density of the fluid is ρ1. Okay, so this liquid flowing from section 1 until section 2. So there is the changes of the area, that is A2, and then the changes of the velocity, that is U2, and also the density may also change, ρ2. So therefore, the mass entering per unit time at section 1 equal to mass leaving per unit time at section 2. So mass flow rate entering at point 1 equal to ρ times area times velocity at point 1, and then mass leaving at point 2 is ρ equal to area at 2 and velocity at 2. So therefore, for steady flow, we have that mass entering the control volume equal to mass leaving the control volume. So by using average velocity V1, V2 and considered incompressible fluid ρ1 equal to ρ2, therefore ρA V1 equal to ρA V2, and we eliminate the ρ because ρ of water is the same, 1000. So the rest A V1 equal to A V2 is remain. So therefore, continuity equation can be declared as Q in equal to Q out. That means the flow rate in equal to the flow rate out. Continuity equation can also be applied to determine the relation between the flows into and out of a junction. So for example, when we have one main pipe inlet that is having the area of A1, velocity V1 and flow rate of Q1. So this pipe, okay, had been separated by two different pipes at the junction. So for the first separation, we have A1, A2, V2 and Q2, and the others pipe we have A3, V3 and Q3. Therefore, the total inflow to junction equal to total outflow from junction. So we have ρ1 times Q1 equal to ρ2 times Q2. So the Q1 equal to Q2. Therefore, Q equal to AV1 equal to Q2 equal to A2 V2. So the ρ here had been eliminated because density of the flow, density of the water is considered the same, that is 1000 for the incompressible fluid. So let's look into this example. So water flowing in 15 mm diameter pipe at velocity of 0.6 meter per second. So at section 1, we have diameter of 15 mm and velocity 1 is 0.6 meter per second. And then we have the water that coming out from the nozzle which is attached to the pipe. So the nozzle has a diameter of 3 mm. So this nozzle have diameter of 3 mm, and what is the velocity that leaving the nozzle? So what is the V2 at section 2? So we have flow in, Q in equal to Q out. So we have section 1 here, okay, and then we have section 2. So 1 is the water that comes into the control volume of the nozzle, and 2 is the water that flowing out, leaving the nozzle. Therefore, the flow in Q1 equal to area of diameter of the A1 and then times with the velocity that moving into the control volume nozzle. So we calculate the area of the section 1 because it is given in the question. The diameter is 15 mm. So we change mm to meter and then we calculate pi d square over 4 times with velocity 1. So velocity 1 is 0.6. So therefore we get the flow rate in Q1 equal to 1.06 times exponent negative 4 meter cube per second. So that we calculate the Q equal to A2 times V2. Since that Q1 equal to Q2, so therefore we can just use the value of Q1 1.06 to be inserted into this Q2. Therefore 1.06 times exponent negative 4 equal to the area of section 2 that is given diameter 3 mm. So we convert to the meter and then we calculate the area of section 2 times with unknown V2 so that we can calculate the velocity 2 and it given 15 meter per second. So let's look to the second example. So the water flows through a pipeline in which the diameter reduced from 500 at A to 300 at B. So A is 500 and B is 300 mm. So the pipe then forks. One branch has a diameter of 150 mm DC and discharge at C, okay, while the other branch with diameter of 200 D, okay, discharge at D. Given that the velocity at A is 2, so this is the velocity at A is 2 and velocity at D is 3.6. So find discharge at C and D and the velocities at B and C. So let's look into this solution. We have the flow rate A equal to area of A times velocity at A. So we calculate the area of A, pi d square over 4. So dA is 0.5. Okay, times with the velocity A is 2. So we get 0.392 meter cube per second. And then we calculate the QD. Okay, so area D, okay, given the diameter is 0.2, so pi d square over 4 times with the velocity D is 3.6. So we get 0.113 meter cube per second. So by having this equation, QA equal to QB, so QA flowing in, okay, at the section A equal to the QB flowing at the section B equal to the QC plus QD. Flow rate that in the QC, B to C, plus flow rate B to D. So QC equal to QA minus QD. So therefore QA 0.392 minus QD 0.113. So we get 0.279 meter cube per second. Therefore, to calculate the VB, so VB, velocity at B, equal to the, so B is QB equal to QA. So we get QA here 0.392. We just put into this equation and times with the area of the B, section B. So we have 5.545 meter per second. And then the last one, to calculate the velocity at C. So we already know that the QC is 0.279. So we just put QC over area C. So area C, diameter of the C is 0.15. So Q over area of C, we have 15.788 meter per second. So let's look into the third example. 3-type discharge water into a large exit pipe as shown in figure. So the diameter D1, D2 and D3, D4 for pipe 1 to 3 are given. Under steady condition, the velocity in pipe 2, so D2 here, velocity 2, V2 is 5 meter per second. And the exit flow rate in pipe 4, Q4, is 200 liter per second. Find the velocity in pipe 1. So, the velocity in pipe 1, if increasing the flow rate Q3, so Q3 increase by 30%, will increase the Q4, will increase the flow rate in pipe 4 by 15%. Okay, so let's look into this solution. So it is given D1, D2, D3 and D4. All the 4 diameters are given, and then we have to calculate the velocity 1, and then it is given the velocity 2 is 5 and the diameter okay, so the flow rate 4 is 0.2 meter cube per second. So stated in the question that flow rate Q3 by 30% will increase Q4 by 15%. So Q3 30% equal to 15% Q4. So 0.3. So 30% is 0.3 Q3 equal to 0.15 Q4. So Q4 flow rate in pipe 4 is given at 0.2. So 0.2. So we rearrange and we get Q3 is 0.1 meter cube per second. So now we calculate the flow rate 2 equal to area 2 times velocity 2. So area 2 is pi j square over 4. And then we just times with the velocity 2 given in the question is 5. So we calculate and get 0.0393 meter cube per second. Therefore, to calculate the total of flow rate Q4, okay, so we have 3 branches of pipe 1, 2, 3. So this flow rate Q in will go to this pipe 4. So Q out at 4. So all these 3 pipe is the total of Q4. So Q1 plus Q2 plus Q3 equal to Q4. So Q1 is unknown, and then Q2 we have already calculated before, 0.0393 plus Q3, that is 0.1. So therefore the Q4 we already known is 0.2. So when we calculate this, you get Q1 equal to 0.061 meter cube per second. So now Q equal to AV, so equal to 0.061. So velocity at V1 can be calculated by using the diameter. So diameter to calculate the area. So V1 is 12.136 meter per second. So that is the answer for velocity 1. Okay, so that's all for topic 5. So thank you very much.